Hi guys, welcome to my video on universal functions. In this video, we'll dive into universal functions and the reasons why Numpy is so important for Python in the data science world. The main reason is that it provides an easy and flexible way to optimize computations on arrays of data. The key to making these computations fast is by using vectorized operations, which we will implement through the use of Numpy's universal functions, also referred to as UFunks. So, this first example here is going to show the slowness of Python, specifically when looping over an array to operate on each element. So what we're going to do is we're going to run this. This is a function we created which uses a loop to compute the reciprocals of the values. So when we run that, it does exactly that. It computes the reciprocals. But now what we have here is we took a big array, np.random.randint, 1 to 100 with a size of 1,000,000, so it's 1,000,000 elements inside of an array, and we're going to use the %timeit operation inside of Python to compute the time required to compute the reciprocals. And so what this does is it gives us 1.94 seconds per loop of that array when using the compute reciprocals function. But when you use the timeit using a vectorized operation, which is just 1 divided by a big array, it's about 400 times faster, and it also computes 100 loops through each time. So it computes much faster than when you use a function in a loop. And that's the difference between using vectorized operations in Numpy versus using a normal loop that you would create inside of Python. So next what we're going to do is we're going to start using some of these UFunks. So we're going to run np.arrange9 reshaped as a 3x3 array 2 ** x. And so ** is just the exponent function. So when we run that, we get 1, 2, 4, 8, 16, 32, 64, 128, 256. So we can also write that as np.power 2, x, and it'll give us the same result. Run that, same result. Now here's a table that lists the arithmetic operators implemented in Numpy, the equivalent U function, and a little description. So you have plus, minus, negation, multiplication, division, floor division, power, exponentiation, and the modulo. So what we're going to do here is Numpy's UFunks feel very natural to use because they use Python's native arithmetic operators. So just the plus operator, the minus operator, the multiplication operator, the division operator, etc. So when we run that, we're using Python's UFunks, but using not the Numpy version of it, just the Python native arithmetic operator. But in Numpy, it works the exact same way. Here's an example of UFunks being strung together to do some standard order of operations math on the array. X is still our array. And so now here what we're going to do, np.add is the same as using plus, right? So np.add, when you run that, that's the UFunk. You could also do x plus 2, and it will return the same value. And the time it takes is approximately the same. So Numpy understands Python's built-in arithmetic operators. It also understands a lot of the functions that are in Python. So what we're going to do here is we're going to use the absolute function. So np.array, that's our array, and then you just take the absolute value of x. You can also use np.absolute or np.abs of x. All work the same way. So another good thing about UFunks is that they can handle absolute values for complex data. So here we have complex numbers: 3 minus 4j, 4 minus 3j, 2 plus 0j, 0 plus 1j. And what this absolute function does is it takes the magnitude. So the magnitude of 3 minus 4j is 3 squared plus minus 4 squared, all square root. So 3 squared is 9, 4 squared is 16. They should return the value 5 for that first value. So it returns 5 for this one, 5 for this one, 2 for this one, and 1 for this one, which are all the magnitudes. So Numpy also comes with a lot of other useful UFunks, and most of the useful ones for data scientists are the trig functions. So here you have the trig functions: sine of theta, np.sine of theta, np.cosine of theta, np.tangent of theta. And when you run that, it simply does that. It computes those sine, cosine, and tangent values of our theta values that we created. So Here we can also use arcsine, arccosine, arctangent. There's tons of useful UFunks inside of NumPy and Python. And so here we're going to use the exponential, and when we run that, 1, 2, 3, e to the 1 is that value, that 2.7182 value, which is e to the x, e to the 1, which is just e. And so also you have the inverse of exponentials, logarithms, etc. You have tons of useful UFunks. Here you can run this. So we're using the log, which is the inverse of an exponent. Also, what you have here, when x is very small, you want to use exp m1, exponential minus 1 of that value, and log of 1 plus that value x. So these functions give more precise values than using the raw np.log function or np.exponential function, which is useful to have in your toolkit because data scientists use exponentials and logs a lot. So when we run that, there they are, they're more precise values, because if you run the log function on this very small x value, it'll actually give you, I believe it'll give you a minus infinity value, because the issue is that the value is too small and the function can't compute it because it's not precise enough. And so here we have many more useful UFunctions, and more info for UFunks can be found on the NumPy and SciPy documentation websites. So literally just go to Google, type in NumPy UFunks, and you can view an endless list of UFunks. Not endless, but there's a lot of them out there. So if you have an issue, a computation you need to solve, something you need to do in NumPy, go there and research it. Documentation is so key when coding. Thanks for watching my video. Please remember to like if you liked the video, dislike if you disliked it, and please consider subscribing. Thanks for watching.